What if we could build AI systems that simply never learn dangerous capabilities in the first place? Today, we're exploring groundbreaking research from Rathi and Alec Radford that shows exactly how to do this. Their paper, Shaping Capabilities with Token-Level Data Filtering, demonstrates a powerful technique for selectively removing unwanted capabilities from language models during pre-training itself. Currently, most approaches to AI safety are applied after training. We train a powerful model, then try to add guardrails through techniques like RLHF or unlearning. But here's the problem. These post-hoc safeguards can be easily bypassed. Adversaries can jailbreak models or fine-tune away the safety training. It's a perpetual cat-and-mouse game. Once a capability exists in a base model, it's extremely hard to truly remove it. The key insight of this research is simple but powerful. Instead of trying to remove capabilities after they exist, prevent them from forming in the first place. How? By carefully filtering what data the model sees during pre-training. Model capabilities directly reflect their training data. If a model never sees certain information during training, it can't develop capabilities around that information. Previous work filtered entire documents containing unwanted content, but this is a blunt instrument. Medical terms might appear in an otherwise benign document about biology. Removing the whole document throws away valuable information. The breakthrough here is token-level filtering. Instead of removing entire documents, we surgically remove just the specific tokens that contribute to unwanted capabilities while preserving everything else. The researchers explored two token filtering strategies. Loss masking removes gradients for target tokens during backpropagation, but lets the model see them during the forward pass. Token removal goes further, replacing target tokens with a special hidden token. Both prevent the model from optimizing to predict those tokens, but removal completely eliminates exposure to the unwanted content. To test these ideas, the researchers used medical knowledge as a proxy for dangerous capabilities. The goal: remove medical capabilities while preserving related biology knowledge. They trained models spanning 2 orders of magnitude, from 61 million to 1.8 billion parameters. They evaluated on multiple benchmarks, including medical licensing exams and free-response medical questions. The results are striking. Token filtering Pareto dominates document filtering. This means it achieves equal reduction in medical capabilities at lower cost to biology and general capabilities. For any level of medical knowledge removed, token filtering preserves more of the desirable knowledge. It's strictly better on the precision recall trade-off. Here's where it gets really interesting. Filtering becomes more effective as you scale up. For the largest 1.8 billion parameter models trained with token removal, the researchers observed a 7,000 times compute slowdown on the medical domain. That means an adversary would need 7,000 times more compute to train a model with equivalent medical capabilities using filtered data. Document filtering achieved only 30 times slowdown. But what about adversarial fine-tuning? Can't someone just fine-tune the filtered model on medical data to recover the capability? Yes, but it's much harder. Compared to RMU, a state-of-the-art unlearning method, token filtering is up to 10 times more robust to adversarial fine-tuning. Models trained on filtered data recover capabilities gradually, while unlearned models collapse almost immediately when fine-tuned. A surprising finding challenges conventional wisdom. You might expect that models need to know dangerous content to properly refuse requests about it. Prior work on toxicity suggested this, but the researchers found the opposite. Models trained with token filtering actually generalize better to refusal training. They learn to refuse medical queries at twice the rate of baseline models, while showing no increase in false refusals. A critical question: how do you identify which tokens to filter? The researchers developed an elegant pipeline using sparse autoencoders. They identified SAE features related to medical content, then used these to label tokens. They found that small, task-specific bidirectional models dramatically outperform large general-purpose models for this classification task. Their 224 million parameter classifier achieved nearly 90% F1 score. What if your labels aren't perfect? Surprisingly, token-level classifiers show strong weak-to-strong generalization. Even when trained on noisy labels, they learn to generalize beyond the noise. You can also trade precision for recall by adjusting classification thresholds. With enough pre-training compute, even aggressive filtering with low-quality classifiers remains highly effective. This research has profound implications for AI safety. For closed models, developers could release filtered versions to the public, while making full models available only through trusted access. The filtering is efficient enough to apply during pre-training without excessive overhead. Most importantly, filtering compounds with post-training safeguards for defense in depth. Important caveats remain. The experiments topped out at 1.8 billion parameters. Very large models might show U-shaped scaling, recovering capabilities from minimal data. The approach uses external classifiers trained on proxy objectives, not perfect attribution of influential tokens. And filtering can't handle dual-use information, where context determines harm. Future work should push scaling further and explore attribution-based filtering. The researchers suggest this approach could extend beyond dangerous capabilities to alignment-relevant filtering. Imagine downsampling self-fulfilling misalignment narratives, or filtering content about evaluation and monitoring that could enable scheming. Token-level precision opens new possibilities for shaping not just what models know, but how they reason about AI and safety itself. Token-level data filtering represents a paradigm shift in AI safety. Rather than the endless cat-and-mouse game of post-hoc patching, we can shape capabilities at their source. The approach is effective, scales favorably, resists attacks, and preserves the ability to align models. As frontier models grow more capable and the stakes rise higher, building safety into the foundation becomes not just attractive, but essential. This paper is available on arXiv, with code at the GitHub link shown. The techniques here could fundamentally change how we approach AI safety. If you found this explanation valuable, consider exploring the full paper for technical details on classifier training, scaling laws, and the complete experimental setup. The future of safe AI may well be built on foundations like these.